Hello, everyone. My name is Jason Evans. I'm an extended reality developer who recently participated in the NASA MarsXR Challenge. The project team would like to thank the Mars Society and Arizona State University for inviting us to speak with you today. Extended reality, also known as XR, is an acronym umbrella term that includes augmented reality, virtual reality, and mixed reality. I saw this NASA Mars XR Challenge as a wonderful opportunity to meet new talented people and to learn Unreal Engine 5, which is a software game development environment typically used for high-end console games, movies, and multimedia production. The project team that was formulated for the challenge created a hazard management system. Okay, I'll just go to the next slide. Before we get started, we would like to acknowledge that Arizona State University's 4 campuses are located in the traditional lands from time immemorial of the Acmeo Odham Pima River people and Peeposh Maricopa, the people, whose care and keeping of these lands allow us to be here today. With this acknowledgement, we honor, affirm, and preserve Indigenous sovereignty and pay our respects to all our relations, past, present, and future. So NASA was looking for XR applications to support research, development, and testing for Mars extravehicular activity operations, also known as EVA, to help better prepare astronauts for training and mission scenarios. I would like to introduce you to the project team, starting with Darlene Villicana, Sanjit Singh, and Valerie Hubner, who unfortunately is unavailable to be here with us today, but we wanted to acknowledge her contributions. Together, we are a multidisciplinary team with complementary skill sets.
All right, so a little bit more about the NASA Mars XR Challenge and some of the requirements. One of them was working with Epic Games' Unreal Engine 5, which is the latest Unreal Engine version, using the Mars XOSS editor, which is mostly like a prefab that comes with preloaded models that we would integrate and use with Unreal in terms of development side of things, using Perforce, which is like another GitHub, but particularly designed for Unreal Engine for open sourcing or pushing and pulling repos, pretty much similar to GitHub, and then virtual reality headsets such as HTC Vive Pro. So the whole inspiration of this project, so when we were brainstorming this idea, we decided to look into particularly planetary extravehicular activities, since it seems like EVA is something that's been going on for a good amount of time, and it seems like a pretty important problem for long duration of space missions. So we decided to look into the risk of EVA due to spacesuit design and concept operation and how we can integrate VR, AR tools for this type of particular problem. And then another thing we looked into was rovers on Mars, how they're already able to detect trash. So we decided to combine this application through heads-up displays where you can do anomalous hazard object detection using computer vision built in through Unreal. And then the whole entire takeaway for this is basically developing a mixed reality data management system, which could be extremely helpful for stuff such as transportations, in terms of like displaying that through like a user interface, or biometrics monitoring, weather management, like it'll detect what's the weather in Mars. Basically something that you can kind of say like an Iron Man helmet display that has a lot of these accurate management systems through like the user interface.
From our project inspiration, we now move to contextualizing it within the EVA landscape. To better design our solution, we needed to better understand the EVA ecosystem and landscape. To create a solution that would support training and mission scenarios for Martian EVAs, we looked at 1, the experiences that NASA has already with planetary spacewalk and what that tells us, and 2, what NASA engineers and scholars have already identified as some of the challenges with Martian EVAs. And these are just some high-level challenges and risks we identified from the literature. We learned that during the Apollo missions, only 14 EVAs were conducted. They ranged from 3 to 9 hours in duration. We learned that EVA operations depended on real-time mission control support, and the distance traversed was very limited. Lastly, we learned that there was a lack of data acquired and analyzed during lunar EVAs, which we see as a missed opportunity. We realized that our design needed to, 1, record and store as much data as possible to leverage for future EVA operations, and 2, address the reliance of Earth-based mission control. Next slide, please.
Yep, it's there.
In contrast, Martian EVAs will be longer. They will also require rethinking EVA operational structures and will involve traversing greater distances. Dr. Andrew Abercrombie from NASA's JSC identified that the frequency of EVAs will increase drastically, about 24 hours of EVA per week, for missions that can last for a short stay 30 days and for a long stay 496 days. Another challenge includes communication delays, which poses a challenge for Earth-dependent EVA operations. Technology gaps have also been identified by NASA. Some of these are actually being addressed through the Moon to Mars framework of the Artemis mission. We realized that at the core, EVA ecosystems will have to change to adapt to very different needs, challenges, and risks of Mars. Our key takeaways for our design solution include rethinking mission control support, which would include increasing autonomy and operational flexibility, which has already been identified by NASA and many other scholars. And 2, develop new technologies to address some of the technology gaps. We decided to approach the MarsXR challenge by conceiving a combination of an artificial intelligence and human-operated Martian mission control support system for real-time EVA intermediary support, or what we call our hazard management system. The key is intermediary, as an understanding of the limited artificial intelligence capabilities and problem solving and the limited number of human users on a Martian mission. We identified that our hazard management system needed to provide real-time hazard information, telemetry and environmental data, a smart systems monitoring, considering that Earth mission control would not be able to do this in real time, live and predictive analytics, terrain mapping, EVA reports, and artificial intelligence knowledge bot. Other capabilities we need to consider include making it scalable, assisting with data management, assisting with mission success, and most importantly, supporting crew safety.
We built a mobile desktop and web application data management pipeline system that interfaces into any extended reality environment, connecting business users who use traditional apps and devices to manage data for end users to receive within any XR environment and vice versa. As you see in this image on the right, we are streaming photorealistic Mars terrain data at the Jezero crater site location that was provided by Buendia for the NASA MarsXR challenge. This data was only available for the hackathon challenge, so we designed our own system as a companion tool that can be integrated into any Unreal Engine or Unity XR environment. This means that we can scale and pivot to support any business use cases that require data management capabilities for XR environments. We created our own XR Mars environment within UE5 to continue building our application beyond the hackathon. Our system is built on Microsoft's .NET 6 framework that supports Blazor MAUI, which is an acronym for Multi-Platform App User Interface. We are able to publish Apple and Android mobile applications, Windows and Mac desktop applications, and a web app from a single code repository that is connected to both SQL and SQLite databases, which are also connected to the Unreal Engine and Unity XR environments. This enables business users to easily manage data through traditional device applications, and that data is made available for the end users on demand within the XR environment. Here is the architecture of the Blazor MAUI application that we designed. On the lower right region of the image is the Unreal Engine and Buendia Mars terrain data being served to the end user within the XR environment. The remaining regions of the framework pertain to the web, mobile, and desktop applications, which are hosted on Microsoft Azure. We are also able to integrate into other game development engines such as Unity to support additional XR devices such as the Microsoft HoloLens. For the sake of the NASA MarsXR challenge, the project team decided to minimize our scope to the Blazor MAUI framework for user authentication and authorization purposes, to establish a data management pipeline to game environments such as Unreal Engine and Unity, and for end users to be served on-demand information provided from our knowledge bot trained on curated EVA and aerospace information to support mission success and astronaut safety. The remaining items have been previously built in other projects, so for the sake of this hackathon project, we remained within project scope, though we do plan to implement these features at a later time. Here are a series of images for the Blazor Maui application to demonstrate user login and registration. New users would need to sign up in order to be authenticated and authorized to utilize the Blazor applications. Once the end user is logged into the Blazor application, there are a number of things that they can do as per our initial project scope. They can interact with the SQL and SQLite databases to manage their data. And here is the telemetry data being streamed within the HoloLens in a mixed reality environment with Unity. End users can be provided with on-demand information on any device, including the Blazor Maui apps or the UE5 and Unity apps, where the knowledge bot would be interfaced as digital humans or other 3D model avatar animated objects. Here's the same knowledge bot integrated with Microsoft Teams. This demonstrates the integration to the Microsoft HoloLens built using Unity.
What type of rock varieties are there on Mars?
On Mars and in meteorites from Mars, we see a variety of rock types: igneous basalt, sedimentary sandstone, mudstone, impactite, evaporites. These rocks are composed of minerals such as olivine, pyroxene, amphiboles, feldspar, carbonates, sulfates, jarosite, gypsum, silica, silicate, phosphates, and iron oxides, hematite.
And of course, the 3D models can be digital humans of both low and high fidelity quality. And then there is the multiplayer aspect of remote users connected anywhere as digital avatar representations of themselves within a mixed reality environment as demonstrated here on the HoloLens.
So when we first got in here, it was kind of a jumble of people. Then we all kind of organized ourselves in a circle and we started introducing each other. And right now we have 3 other people here.
So the overall market study that we conducted, we see that the global market for aerospace industry, particularly XR, it's really growing. And by 2026, it's expected to be a $5.8 billion market with a 37.9 compound annual growth rate. And then some of the customers that we plan on speaking with. So we plan on speaking with private sectors such as space agencies like NASA, and then also new space corporations that focus in areas like space tourism or suppliers for spacecrafts or space mining companies. And then public sectors would be advocacies like, for example, the Mars Society, or places that are really big advocate for mission to Mars, universities such as professors that do a lot of aeronautical research on spacesuits or heads-up displays, public education groups, and then the AFWorks committee, which is a Space Force committee that's focusing a lot on space exploration and partnering with NASA and the Air Force. And then some of the competitors that we have. So we looked into, and NASA apparently in some ways happens to be a competitor in terms of developing head-mounted displays for situational awareness in real-time exploration, such as integrating real-time biofeedback displays through the helmet, or caution and warning systems and static images of EV locations through a lot of their technologies. And then Coda Octopus is another company that's working on management system for defense and commercial operations. And then another company we look into, which recently is adapting to AR, is Oceaneering. And they're mainly trying to develop AR for remote astronaut, for spacesuits and EVA tools, particularly for training. And while these are competitors, in some ways we see competitors also as customers, because in ways it helps us understand the capabilities of current systems, what's really missing and what are some of the lackages, and how we can fill in that gap.
The vision of the XR data pipeline integration from the Blazor Maui app needs to be communicated to audiences unfamiliar to extended reality while we are in the process of developing these features within Unreal Engine and Unity. We utilize an AI text-to-image processing service to prompt the model to generate images based on descriptive text for instant communication of concepts to bring others up to speed as to what we are building. In these series of images, you can see an astronaut end user on Mars interacting with mixed reality objects overlaid in their physical environment for data querying and visualization purposes. Here you can see the planned computer vision feature for object detection using bounding boxes to mark regions of interest. Some of our current limitations building this cutting edge technology is with our hardware, including access to new generation XR headsets, laptops, desktops, GPUs, software paid licenses. There's also a learning curve for the game development engines and source control tools. XR safety and ethics is always most important to us as we strive to increase human performance within XR environments aided by AI capability and features. Building XR technology is expensive, so cost and external support is important to us. We wish to conduct human-in-the-loop testing, so we need access to aerospace subject matter experts and other people knowledgeable with XR technology.
So these are some of the funding opportunities that we looked into. And since we're really interested in commercializing, we decided that, we're gonna apply for the Epic Games Mega Grant Challenge. And also, for other opportunities we're looking at is also the NASA I-Corps program, and then SBIR and STTR, particularly because we're really interested in commercializing the technology. And then we're also considering looking into agencies such as Canadian Space Agency and the European Space Agency. And these are some of the established collaborations that we currently have, such as Eurenics, Mars Society and MXT Reality, particularly with James Burke and Jeff Rayner, MIT Sandbox, NVIDIA Inception Program, Google Startups, Microsoft Startups, Amazon CTO Fellowship, University of Toronto, Queen's University. And then potential collaborations that we hope, or is the goal that we additionally want to land with, such as the MIT Space Exploration Initiative Group, which is part of the MIT Media Lab, MIT Human Systems Lab, University of Auckland, particularly with the Empathic Computing Lab, University of Southern California, University of Washington Reality Labs, and AFWorks. And beyond the MarsXR challenge, really we see other areas that we can really utilize our direction with the XR approach, such as EVA training for operational EVAs. Particularly what we see is beyond just VR, we want to apply kind of these similar technology applications, but for real-time operation. And that's where AR comes in. And we plan on, releasing a lot of this stuff as AR interfaces as well for Microsoft HoloLens 2 device. And then also for lunar and low Earth orbital applications, such as space tourism and ISS and gateways. Also space prosthetics, that's something huge and recently we came across. And then also IoT and robotics applications, such as, how we can anticipate robotics training to simulation or controlling a real robot through a device. Such as a head-mounted display device, and then also looking into the ethics of mission to Mars. And then some of the lessons we learned, such as team formation, because we all come from different backgrounds, so we learned how we can really combine our background into doing something that's so cool and amazing, that's really impactful, and that was some really amazing experience.
Default SQL plugins that ship with Unreal Engine 5, there are limitations as it is up to the developer to clean up memory allocations, build out operations from scratch, and loop over result data for readout values. GitHub did not work for us for the Unreal Engine 5 project as it was close to 100 gigabytes in size for source control. We had to learn Perforce and configured our Azure environment accordingly. This presented challenges for us and caused delays within our development cycles as we had to consult with source control experts elsewhere for assistance.
Next steps include conducting expert user research and user evaluation and continuing the development of our solution. We will be designing an expert user study to help us define requirements for the database, define function allocation, and inform the interface design, but also we want to research the ethics of artificial intelligence and astronaut safety. Once we have a new iteration of our hazard management system, we will conduct user evaluation to evaluate performance, usability, workload, feasibility, and safety, and obtain expert user feedback for the next iteration of our hazard management system.
Today, we are asking for your support for this project if you wish to see it continued to support the hazard management needs of EVA operational activities on Mars. We are starting a Kickstarter campaign. We are looking for project contributors, mentorship, and sponsorship in any way, shape, or form to make this a success. You can kindly contact us if interested, and do keep an eye on this project. Please follow our Twitter page for once we launch our Kickstarter campaign, and do be in touch if you want to reach out. Thank you for your time today. Here are some of the resources we used, and here are the references for this presentation. We are happy to answer any of your questions.
Hi, I was curious what kind of headsets you were supporting with this.
Absolutely. Yeah, great question. So for the hackathon project, since we were using Unreal Engine 5 and the NASA supplied XOS editor for the photorealistic Mars terrain, we were limited to virtual reality, which included, we were constrained to the HTC Vive, the Valve Index, and other headsets would work, like the Oculus and the Windows mixed reality headset, but the hand controls wouldn't work properly. So for the sake of that hackathon project, it was specifically the HTC Vive and the Valve Index. However, for some of the other applications that we demoed for the mixed reality and augmented reality, we support a wide range of devices: HoloLens 1, HoloLens 2, Windows mixed reality headsets. We can push out to other additional endpoints such as Oculus, Oculus Quest 2, and then of course the HTC Vive Valve Index. And then on top of it, for augmented reality purpose, we can also stream through mobile apps on connected Android and mobile Apple devices. Well, thank you everyone for your time today. And once again, it was a pleasure to be here today, and we wish you to enjoy the rest of this conference. Bye-bye.
Thank you, everybody.
Thank you.